So now I have to switch in English. I would like to present Dr. Jean-Jacques Favier of the French Space Agency. A few words on his career so far. Dr. Jean-Jacques Favier is an engineer. He graduated from the Institut Polytechnique de Grenoble. He got his first PhD in metallurgy. That was from the École des Mines de Paris in Paris. Then he was granted a solid-state physics PhD, so his second PhD, from the University of Grenoble. That was in 1977. He joined the Nuclear Research Center of Grenoble as a researcher in materials science, his prime sector of research. And then he became a director of solidification laboratory, and finally, director of research of the French Atomic Energy Commission. He contributed to the preparation of more than a dozen of space experiments in collaboration with different space agencies, among which, of course, the French Space Agency, the European Space Agency, the Soviet Space Agency at that time, as well as NASA, the American Space Agency. He's the founder of the Mephisto program. I think he will share this experience with us in his presentation tonight. That's a metallurgy experiment which flew 4 times aboard the Space Shuttle, Columbia. He was selected as an astronaut candidate by CNES, the French Space Agency, in 1985, and subsequently he was selected as a payload specialist by NASA. That's actually the astronauts that run the experiments in the Space Shuttle. That was in 1992, if I'm not mistaken. He became a backup crew member on the Spacelab mission, IML-2 in 1994, and eventually he did fly as prime crew member on the LMS mission in 1996 aboard the Space Shuttle Columbia for a 17 days mission. So back in France, Jean-Jacques Favier was successfully deputy director for space technologies at the French Space Agency, and then the deputy director for strategy and advanced concepts. He has also been appointed full professor and research program director at the International Space University in Strasbourg, in France. He's an author or co-author of more than 150 publications in peer-reviewed journals or international conferences. He has also been appointed, he's one of the patrons of the French Technical and Scientific Framework on Habitats and Extreme Conditions, and that's also sponsored by the French Ministry. Dr. Favier, we are very happy to welcome you tonight. We're very happy that you're here to enrich this conference with your experience, and I pass the floor to you. Thank you.
Thank you. Good afternoon, everyone. Good evening, by the way. Thank you, Adrianos, for this kind words on in introduction me to you tonight. So I better understand now, looking at your faces, very young people, most of you, why actually the organizer asked me to talk about my life as a student also. And the story that I want to tell you tonight is something a little bit unique in the sense that actually I worked on a particular topic. I will tell you a little bit about it tonight. And I was able actually to continue working on this with space agencies up to the point that I was able to develop a particular program. We call it Mephisto, and a particular instrument which flew 4 times. And on the top of that, there was a cherry on the cake. Once I was able to fly myself with my own experiment, and I was able actually to perform my own science in space, which is very rare, by the way. So you have a lot of astronauts flying who have flown. Do you know about how many astronauts went to space already from the very beginning of the program? 150, 100, 200, 400? How many? Actually, more than 500, okay? But among these numbers, just a few of us are scientists who perform their own science on board, you know? Maybe maybe two or three names. not more than that. So on these pictures, you see actually two pictures of a device. This was my first experiment that I have developed when I was a student for my PhD. And I will tell you the story. 25 years later, actually, I was able to fly myself with an experiment which was actually just a follow-up of my own PhD experiment. Okay? So this is a little bit crazy, but I want to tell you why. So being here in Thessaloniki, so the home of Aristotle, so I want to say that I'm very honored actually to be able to present my science here because Aristotle is considered as the father of the modern science in the Western world. And he was also a philosopher, that I am not. And he used to say a few sentences like this one I like, which says that there is no genius without a grain of madness. Okay, I'm not talking of me as a genius, but as someone having some grain of madness. Because if you want to realize your dream, okay, you have some time to have a grain of madness. Okay. So what I want to talk about tonight, maybe in 4 different parts, will be the level of the studies I did as a student to get my PhD degree. And here you have just a picture of my manuscript. This was in 1977, which is basically 40 years ago already. Okay, and why? Based on the work I've done at that level, I was able in the 80s to propose a program, the Mephisto program, working on the same topics, which was related to the study of crystallization and using a new technique. And this technique, which is the thermoelectric technique, actually has been proposed to the space agencies, CNES and NASA, for the Mephisto program. And then I will talk a little bit about my flight myself with nice pictures, because being over there is something very unique. I can tell you, when you look down at the Earth and at the sky, this is really something very special. But I was not there only to look at the window. I was there to work on my experiments, and this is what I will show you. And finally, which is something rather unique. So I've proposed a program. I've prepared in my lab with my team an instrument. I flew it, and after the flight, with my team actually, we have made the full analysis and publication of these spaceborne results. So I made actually the full circle. And I want to show you this as an example, because for you guys, if you are, and I'm sure you are, interested by science, okay, or engineering or technology or whatever, okay, you will get a lot of reward because making research is something that makes you happy every day, I can tell you. And even in some cases like this one, which can dream to something and fulfill your dream. So, just a few words about the science itself to show you. So we were talking just before about the need of having smaller and smaller microelectronics and antennas, but this supposes that the matter, the semiconductors material, should be very well defined, and when we produce these items, you know, and therefore you have to understand what happens at the atomic level during the process. To make it very simple, okay, I took the case of just a binary alloy, metallic alloy, or a semiconductor with doping. So you have to remember two things. In order to get it, you have to follow the rules of the thermodynamics, okay? So we call that the phase diagram. So, and you have here some relevant parameters as a function of composition and so on, etc. Now, for the process itself, So you are crystallizing from a melt, for instance, and the melt is under a thermal gradient, okay? This part is hotter than this one here, and because we are under the gravity field here on Earth, this causes convection in the liquid, okay? And I will show you that if someone can press for me on the pictures. First on this one, yes? You see that depending on the conditions, the gross conditions, due to the presence of gravity, you don't get stabilized conditions for the growth. Therefore, you are producing defect in your crystals, okay? And you see it here. This is the thermal field, the temperature which is varying. And if you just can make it with a blue simulation also here, you see that the concentration of the sample that you are getting is not homogeneous, and this is not what you need actually to make these new devices, okay? So you have to understand why and how to be able actually to overcome this kind of phenomena, okay? So, as a consequence of this, depending on the scale, either you get, like here, this is a sample which has been cut, the striations or concentration differences between point and point, which is not good. And in metallurgy at the macro scale, you can get structures like this one, which are not, obviously not homogeneous, therefore not so good in terms of use. So, how to be able to manage the conditions at a solid-liquid interface, or at least to measure what happens as a function of the conditions, the growth conditions, and how to modelize this in order later on to be able to find the best conditions for the growth and therefore for the production of the antennas and so on. Okay? So what I have developed in my thesis at the time was a new technique which allowed me to measure the temperature at the solid-liquid interface here. Okay? Here you have a setup with a solid, the liquid here, the same on the other side, and I was just measuring the voltage between the two ends of the solids. So the two ends of the solids, this gives me the measurements of the difference in temperature between the two interfaces. One was at rest, this was its thermodynamic temperature. The other one was growing, meaning actually difference, the undercooling I've presented before, between the two. This was a very simple way, you know. The problem is that, in general, the solid-liquid interface in metals are very bad thermocouples in the sense that what you call the Seebeck coefficient, the voltage that the junction can produce is very low, of the order of 1 microvolt per degree. And more than that, the undercooling, the difference between the two temperatures you want to measure, is very low also, less than 1 degree. So at the end, you have to measure in the range of 50 nanovolts to 1 microvolts in very bad conditions, in the sense that you have a lot of furnaces, therefore of disturbances because of the environment. The conditions are very severe. And I'm talking now from the 70s, when I was actually like you, a student. And in the 70s, we didn't know what an electronic microvoltmeter was, didn't exist at that time. The only way to measure very low voltages was with a galvanometer. I don't know if you remember what a galvanometer is, okay? This is actually a device on which you are measuring the voltages by the deformation of the position of a loop, okay, and which is suspended by a wire. So any vibration when just working around the experiment was enough actually to move the signal. So it was very difficult to measure in the 70s voltages like this. Hopefully now it's much, much easier. But at that time, the only way to make that was to use galvanometers. And here you have the setup of my thesis, you know. look at the scale, this half a meter, meaning that overall, you will see a picture of it, to make this loop, you remember, with the two interfaces and the measurement of the voltage by the galvanometer here. This actually was 3 meters on 2 meters, you know, it's a very, very big thing. So impossible to think of flying something like this later. So look, this was my first my experiment for my thesis, and so you see how big it is. It was actually using actually the room over there just for the single experiment. Okay, so. But it worked, and I don't want to go too much in details, but just to show you that the Seebeck voltage, okay, I was able to measure as a function, for instance, of the velocity, gross velocity, was actually able to characterize a kind of solid-liquid interfaces and instabilities between these two cases for two different velocities, and at the end, the Seebeck voltage, steady voltage, actually looks like this with different regimes. At low velocity in this one, actually the voltage was affected by the presence of gravity because of the convection. So this was the main results, and I wanted to continue working on this later on, but at that time I had no idea about the potential of space, the potential of microgravity conditions. I don't know if you heard about this word, microgravity. You know what gravity is, of course. Micro, you are Greek, so you know what it means. It means very small gravity level, residual levels, okay? And the only way to get microgravity conditions is to be in free fall all the time, okay? In free fall, when, for instance, the space station or the shuttle is orbiting the Earth, it stays in orbit because it's free-falling every time. So everything inside is free-falling, including the astronauts, of course, meaning that they are floating inside the shuttle, okay? So this was the beginning of the microgravity program. It started in the early 70s. Remember my thesis, I defended my thesis in 77. Okay, it was just the beginning of the program. So the Apollo program, you know all what the Apollo program is and means. This was at the very beginning of the 70s, between 69 and 73, okay? And these guys, I mean the astronauts on board Apollo, and the Russians also, or Soviets at that time, about Soyuz, experienced the microgravity conditions, okay? And they started making some experiments just to check what it means in terms of impact on some material processing, for instance. And based on that, so the main space agencies, the Soviet, NASA, the ESA, European Space Agency, okay, considered that these conditions were very unique in orbit in order to get these microgravity conditions. And the potential of these microgravity conditions is very big in certain disciplines like the one I'm talking about. So Europe decided to develop a special laboratory called Spacelab, which flew on the Space Shuttle Columbia during about 15 years. So we had dedicated flights for science and microgravity during the shuttle era, during this program. As you know, probably, the shuttle program has been terminated because of a big accident of the Columbia, the one I flew on, you know. And so now we have the ISS, the International Space Station, which is the largest ever built space laboratory, which benefits of microgravity conditions, but something, because you are actually physicists, you should know that if you actually develop too big or too large laboratories, which is orbiting the Earth, which is supposed to be in real 0G, actually any vibrations of the structure and the structure of the ISS is vibrating a lot because, you know, the two big solar panels they have on the space station are big as a football field. Can you imagine the size, you know? So this one is vibrating a lot, and we used to say that the space station is a bird which is flying with the two solar panels, just like this. This is funny. It's not so funny for science because this induces gravity levels, okay, these motions, and therefore the residual gravity level is not as good as it was on the Spacelab, which was a tiny laboratory on the space shuttle. So this Spacelab and shuttle era was actually the best time for microgravity studies. So just to remind you the kind of research which can take advantage of microgravity. So every time you have what I have explained before, liquid phases or gases under a thermal gradient, therefore the density, local density is different from one point to the other. So therefore you induce convection, and this convection can be unstable as I showed you on the simulation. And this is not good for the processes or for the measurements of some parameters, okay? So gravity is responsible for buoyancy, and now if you go into space, so you can reduce this gravity, and therefore you get some kind of ideal conditions to study phenomena or even to produce soft materials. The other statement here say that well, the physics is the same in space and on Earth, okay? But when being in zero-G conditions, actually, this is a unique conditions where you can suppress this gravity parameter that we have to live with here on Earth, okay? This is the only place where you can suppress this parameter, okay? When I say that, I'm not completely right because just for your reference, in a drop tube or drop tower like this one, and this one have been developed in the 19th century actually, people have already understood at the time that actually melting lead at the top of it, okay, through a sieve here with a small holes, you can form drops which will free fall, okay? And because they are free falling, no effect of gravity during this period, okay, you obtain very spherical spheres like this here, okay? And if you solidify it before they reach the base here, so you can get very nice spherical shots, you know. And you see, the first one was built in the very late 80s in the United States, in England, and a few years later in the United States. This was the tallest structure in the US at that time, with something like, let's say, 80 meters, okay? This was built especially to get microgravity conditions, but during a very short period of time, of course, less than 3 seconds. So if you want to get long duration gravity levels, you have to go in space and to orbit the Earth or another planet. So I was talking about the grain of madness just before. My grain of madness was this one here. So I had actually proposed a way to measure very thin temperature difference at the solid liquid interface to better understand and control the growth process, okay? I showed you that on Earth, when you make this kind of experiments, you have disturbances coming from gravity, okay? So why not to fly this kind of experiments in space and to propose them to space agencies, what I call the CBEC technique, for monitoring solidification experiments in space, because the space program will need to know exactly what happens at the solid-liquid interface during growth. And this is what I did, but when I did it, I was almost sure that the space agencies will not react, because I was just a scientist with no possibility, no possibility actually to interfere on decisions. But I did it, and I was lucky that these space agencies actually understood the interest of this kind of technique for the space program, and they accepted it. Okay, so after my thesis, I went to the CEA, the French Atomic Energy Commission. I was working on the CBEC to try actually to reduce the size of, you remember the big experience, the size of my experience for my thesis. And at the time, we had the first the microvoltmeters coming in, so it was good for me. And I've been hired actually also to prepare some experiments for the space agencies. Okay? So I was closer and closer from NASA, which was actually my goal. So what we have developed, you remember maybe that I had a U kind of shape CBEC circuit for my thesis, but we have developed here a linear run, but still on the same principle, two cold ends here, solid, and liquid in between. One stays at rest, which is a thermodynamic equilibrium temperature, and this one is moving back and forth. Therefore, the temperature of the interface at this point is changing, and therefore can be monitored. So this was possible now because we had to make sure that the temperatures of the two ends of the solids, you remember they were together on my thesis, were now sufficiently well controlled because of the progress of microelectronics. So the big setup that you saw for my thesis, which was 3 on 3 meters, okay, we were able actually to make it smaller and smaller, and the size of these instruments is something like 1 meter long here and 40 centimeters in diameter, with actually the same capabilities and even better, because the electronics evolved during this time, better than what I have done before. Okay? So again, this program has been proposed to the French agencies, and I was able to negotiate an agreement between France and the US to develop 2 flight models, which have been developed by France, and NASA actually was committed to fly it up to 6 times for free, and this was a good deal for us, because flying on a space shuttle or in space in general is very expensive. Same time, 85, okay? The space agencies, the French one, CNES, but also NASA, opened the selection of astronauts to non-pilot, because I'm not a pilot myself, but opened the selection to engineers and to scientists. So I applied, saying, well, why not me? Because this is closer to my profile. And I was lucky enough to be selected by France in 1985. Okay, so I was scientific candidate astronaut, which doesn't mean that I will certainly fly next year, okay? But at least I was shortlisted to fly. The question after was to be able to find an opportunity to fly. In France, we were selected to fly either with the Russians, or Soviet still at the time, and the Americans, okay? So I have been selected for both of them. After my first training in the Star City, in Moscow, the place where actually they are training the cosmonaut, after about 4 weeks, they discovered that I was too tall, actually, to get in the Soyuz. Okay, this is incredible because I went through so many tests, you know. At the end, in order to select us, I didn't know what to measure on it, on us, you know, brain activity, cardiovascular, and whatever. So they just neglected to measure my leg, and I was 2 centimeters. It was 2 centimeters too long. So they told me, "Sorry, guy, you cannot fly with us on the Soyuz." What I have to mention today, for Adrianos in particular, because he knows very well all these things. Now the Russians have changed the seat of the Soyuz because there are a lot of Europeans and Americans who are tall like me. Not exactly like me, because I'm still the tallest astronaut of the program, you know, but close to me. And now I could fly with the Soyuz, you know, in a new seat, okay? But at the time, no way. So I said, well, how to fly? In Europe, we expected to get the Hermes program, which was a small shuttle to put on top of the Ariane 5. But in 1986, maybe you remember, or you know the date, maybe you remember, I'm talking to the seniors here in this room. The shuttle program had a very big accident, the Challenger accident, okay? So we lost all the crew, and therefore Europe decided to stop the Hermes program because it was too dangerous, and it was very expensive. Okay, so for me, because I still wanted actually to fly as a scientist with my experiments, the only way actually to get a chance was actually to move to the US, okay? So I asked my boss if I could make a sabbatical year within NASA in a lab, okay, because I was already recognized as a scientist. And so I went to the Marshall Space Flight Center in Alabama, and I was working with some of my colleagues on the shuttle program. I was in Alabama since about 3 months when NASA decided to open a new selection for scientists. So I applied again, and I was lucky to be selected this time. Yes, so I was closer and closer to my flight, okay? And at the same time, I was working on the Mephisto. You see the Mephisto? It's this canister which is placed outside on a shuttle cargo bay. So I was here working on it, and this is the selection of 85 in France at the CNES level. So you see I was the tallest one, okay? And, but nevertheless, so I was able to fly later, as you know now, okay? Closer and closer, so selected now by NASA, but not as prime in a crew, but as a backup, okay? And NASA told me, do you want to be the backup on the next mission or not? Well, I said, well, I have to say yes, of course, because this was actually needed before getting a prime on a mission to start to be backup. And I was closer and closer again from the Astronaut program and so on. So I was working and training for 2.5 years in Houston, okay? I was working with famous people like John Young. You remember this name? Maybe you know this name. This guy, an American astronaut, he made all the phases of the American space programs. He landed on the moon. He walked on the moon. Okay, and after that, he was the first to pilot the Space Shuttle Columbia. Okay, this guy was just amazing. And having John as an instructor, being at Houston, was something very special, I can tell you. Okay, so this is what I did for a mission up to the last medical check before the flight. The number 1 was okay, so I didn't fly this time. I just waved them at Kennedy Space Center. But, well, I was expecting to be on the next mission. And this is what happened, actually. So, I was with NASA from 22 to 27. As I just explained to you, I was back up on this mission. So this is the reason why my name is not on the patch, okay? but I worked and I trained with all these people. During the mission, what was very interesting for me, actually, NASA asked me to be the guy from the control center talking to the crew, you know. Did you see the Apollo 13 movie? Okay. You remember the guy who was talking to the astronauts on Apollo 13? And Apollo 13 was in a bad shape because they had a big trouble. Houston, we have a problem. Okay. So I was, from this mission for IML, I was the guy talking, they call it now Capcom, okay? Talking to the crew. And this made sense because I had 2.5 years training with them. I know them, we were very good friends. And I was supposed to do myself the experiment that these guys were doing on board. So I was able to tell them to do more or to change things, etc., parameters. And so I did this job, which was very, very exciting one. I was really part of the mission. The only difference between these guys, the crew, and myself, they were floating around in space in the shuttle. I was sitting on my seat on the control center, but it was a very great experience. And 6 months later, the general administrator of NASA called me and said, "Do you want to be prime on the next mission?" I say, "Of course." No way, no hesitation, etc. And so I went through another training of 2.5 years on STS-70A. STS means Space Transportation System, which is the nickname of the shuttle at the time, number 78. And I flew on the LMS mission, which means Life in Microgravity Spacelab. Okay, and this time my name is on the badge. Okay, and so I flew. This was a period when I was in training, and I flew in 1996. So now I just want to show you a few nice pictures. I like them, of course, because this is part of my life, you know. But I think I would like to share it with you. This is the shuttle. It looks at the just before takeoff, you know. This shuttle was very dangerous, you know. We had 2 big accidents. The Challenger in '86 and Columbia also. The one I used myself actually has been destroyed in 2003. And we lost the 2 crew, 14 people, you know. So very dangerous. But from a technical engineering point of view, the shuttle is something very special, you know. It is like this on the launch pad, just like a rocket, okay? In space, it is like a small space station, floating and so on. And for landing actually, it just landed like an airplane, okay, on a track. So all the technologies of the 3 main vehicles are put together on the same vehicle. This is why actually it was so difficult to make sure that all will work together. Just give you an example. For landing, you will see one slide later, we need wheels, of course, with tires, okay? By the way, which were French tires, Michelin, okay? But worked very well. But imagine, these tires have to be at the right pressure at the moment of landing, of course. But during all the steps, the launch, then the orbits, so the tires and the wheels were submitted to all these vibrations, the difference in temperature between the cold part and the sunny part. So I don't know if you realize, when because outside in orbit, there is no atmosphere anymore. Okay, when you are in the shadow, the temperature is minus 150 degrees Celsius. Okay, when you're in the sun, it is plus 150. So 300 degrees difference. And remember, I thought about that several times when I was in space. Well, we have tires here, okay, and we want to make sure that we have the right conditions for landing. So just an example of when you mix technologies like this on the same vehicles, it is very hard actually to control all the parameters and make sure that everything will be safe. And unfortunately, as you know, we lost 2 shuttles. So, 1996, the Microgravity Spacelab mission, STS-78. So, we were at June 20th in Cape Canaveral, Florida. This was, remember, 11 years after my first selection. So it took me 11 years between the time I've been selected in France and my flight. And here again, I am the tallest one here. Easy to recognize. But I was actually able to fly in the shuttle because the shuttle has more room for legs. Okay. So June 20th, just on the clock, at the opening of the launch window. So we're lucky actually to get launched, okay, take off and so on. And I don't know if you can realize, maybe you saw already some movies or pictures or whatever, but the crew is just here. I was seated here, and I was just on the top of a big rocket like this, with a solid rocket, and here 3 main engines, a lot of vibrations and everything. But it takes just 8 minutes, okay, to get from the ground, from Cape Canaveral in Florida, to the orbit. 8 minutes, that's just nothing. Imagine 8 minutes. In Paris, it's 3 stations of metro, for instance, and so on. And you pass from the zero velocity to, in order to be able to orbit, 28,000 kilometers an hour. Mach 25, you know. So you can imagine a kind of pressure under which we are during these 8 minutes. But at the end, when you are in orbit, so the commander cut off the engines, and at this particular moment, we were just floating, okay? No pressure anymore. And I was floating around like this, looking at the window, of course, because it was so nice. And this is what I saw for the first time. This is the North Atlantic on sunrise. Here you have the sun, okay? The white part here are the clouds, okay? But I like this picture that I took myself, because this is one of rare pictures where you see very clearly the day-night line here. You see, this part was day of the planet was day. This one was night, and you can even see the line of the twilight line. You know, meaning in this part it is not completely dark, but you cannot see the sun anymore. Okay, so this is very well pictured here. Okay. Very beautiful. So when I saw that at the window, I said, well, this time is not a training anymore, it's not a simulation, I will really be in space. And one of the better paths as a European, of course, I liked this one. I will show you. You organize this place, of course. You organize this place, of course? No? Yeah, exactly. This is Gibraltar. Yeah, okay. Spain here, Africa, Morocco here. So I used to take my coffee early in the morning, my breakfast coffee, where we were passing over Gibraltar, okay? 2.5 minutes later, we were already there, okay? Another minute, here we are. I selected this one just for you. and you see where we are here, very clearly visible, okay? And another minute later, we were already here, the end of the Mediterranean Sea. So it took us 5 minutes to go from Gibraltar to Israel, okay? So I didn't finish my cup of coffee and we were already there. Okay, and you see how beautiful are these pictures, of course. Here you see, the shadow of the tail of the shuttle, And so every time I was able to find some time for myself, of course, I went at the window to look and take pictures. Okay, and most of the astronauts do the same, of course. Well, I liked also to look on the other side to the dark sky, and here to the moon, you know. So the moon is not bigger than we used to see it from the Earth, because we are not far, we are just 400 kilometers away from our planet. But we are over the atmosphere. There is no deformation of the stars, of the planets when we are in space. So it was very easy to see the different so-called mare and continents on the moon from the shuttle, from the orbit, and I like that also. Okay. Of course, now talking about work, of course, I went there to work. So in the shuttle cargo bay, we had this the Spacelab module, which is this one, which is pressurized module, meaning that you don't need to take an extravehicular suit to get outside. Outside here, it's a pure vacuum, okay? But inside, we have a tunnel to go from the shuttle to the Spacelab. You will see how it is inside. And we had also this structure outside where my Mephisto was placed, okay? Why to put it outside? Just because in order to make sure that we don't have effect of convection around the furnace was built to be under vacuum, okay? And instead of actually bringing with us pumps in the Spacelab in order to get vacuum, we just placed the Mephisto instrument outside and opened the valve here to get the space vacuum in the instrument. Okay? So inside it's just like a normal laboratory, okay? So I was doing my experiment. I was in charge of 43 different experiments here, and my commander was Tom was coming from time to time to see if I was working properly or not. So, but this was just for me the continuation of my research I used to do in my lab, okay? So I was very pleased with that. For instance, here we have a furnace in which I put some samples in, control temperature and so on. And because I knew the experiments, I was able to actually optimize myself the parameters of the experiments, which is not the case when you have astronauts like today on a space station, which are just pushing on and off experiments. So they don't know exactly what they are looking for. They had training for that. It's not their fault, but this is the way the program has evolved. But at the Spacelab time, so the scientists were able to change them the problem. So it was just like in my lab. The only difference here is I was able to make some experiments upside down. There's no difference between top and bottom. Something I cannot do in my lab, okay? And because we were very busy, we were 7 at the same time in this module, so we have to optimize the volumes. This is what I was doing here. And like just in the lab, actually we got some failures on some instruments, and because we knew exactly how the instruments were built, so we were able to repair the malfunctions. These experiments, as all the space material, is tested and tested and tested by engineers on the ground. Well, they accept actually to write down procedures for what they call malfunctions in case there is a problem. So we have a book where we are supposed to see the way to actually repair the experiments. And of course, what happens in reality is never in the book, okay? So you have to invent yourself, you have to talk to the control center to find the solution. I can give you funny examples about things like this later if you are interested. So having astronauts on board, and especially specialists of the different sciences, is very important for the program. Now for the Mephisto, you remember it was outside, so I was unable to move, to change things. The way I communicated with this instrument, with the others outside, was through a computer only. So I was here, I'm in the cockpit, on the commander seat, by the way. But actually, here, you cannot see it maybe. There's a laptop, so I was able to change my parameters and to optimize experiments from the cockpit to the experiments outside. Okay, so I can continue hours talking about my mission, of course, but I just wanted to present you some of the results to show you on at least 2 of the 4 flights of Mephisto how good were the conditions, microgravity conditions, and here we are measuring actually the function of time, the Seebeck, you remember the Seebeck thing, the Seebeck measurements as a function of velocities and so on. So you have actually the experimental points corresponding to different velocities, and the full line is the modeling. So we were able to model with an error less than 1.38%, 149 here, 1.07, which was not achievable at all or in my lab on the Earth. So this is a kind of very good experiments that we got into space. I can discuss, if you are interested, other results that we get. Just give you here maybe some explanation on this. So I told you that in space, in an orbital spacecraft, the gravity level is not exactly 0 because of vibrations, because of the motion of the astronaut inside, which can actually induce some gravity levels. What happens also when the shuttle or the space station is maneuvering in space, in orbit, for different kinds of reasons. So the commander actually is firing some small motors in order to get a new position of the shuttle or whatever. So here you have the impact of 2 maneuvers of the shuttle in terms of Seebeck. You remember this kind of very fine measurements. And we were able to see, on the Seebeck the effect. So I was asking the commander to make a maneuver, and at the same time I was looking at my Seebeck signal. So this was actually what we saw, and this is the simulation that we made by modeling later on, which corresponds very clearly to what happened. So just keep in mind that we were supposed to be in 0G in space, but for reasons I have mentioned before, the size of the space stations, for instance, etc., we are not exactly. But when we are maneuvering, okay, we have impact also the gravity level. And thanks to the Seebeck measurements on Mephisto, we were able actually to quantify all these things. Well, to finish up with that, I'm very proud of this, because 18 years after the first Mephisto flight, okay, 44 years after the first Seebeck measurements for my thesis, you still have people, and these are scientists from my previous lab, working and using actually the database that I was able to make in space for actually their own work, you know. This work, for instance, has been published just 2 years ago. So 18 years after the measurements, the database that we produce in space, thanks to the absence of gravity and so on, is still used for good science. And this is, of course, very rewarding. So as a conclusion, I showed you that at the beginning I was an engineer and a metallurgist, okay. I wanted to make research because I thought that this was what I wanted to do, okay. I made a PhD, okay. I invented this Seebeck, you remember, measurements for solidification control. Okay, 15 years later, we were able actually to develop this very compact experiment on the same principle. And myself, I was able to fly as a scientist on the Space Shuttle Columbia with Mephisto on board. So this is very rewarding, you know, a long way from the very beginning to that final slide. And just to tell you, I'm talking to the young generation, okay? If you have a dream, you never know what will happen, okay? If you have a dream, try to keep it in mind and never give up, okay? This was more or less the case with me here, okay? At the very beginning, I didn't know that I will fly as an astronaut, okay? I was interested by engineering and science. Then came some opportunities. I tried to grab them, and at the end, I succeeded, okay? So, a summary on the microgravity aspect of things. In the 70s, it started with the Apollo Soyuz program. I mentioned that already. Really, the golden age of microgravity science was during the Shuttle age in the 80s and 90s. And I was lucky, actually, to be part of it, okay? We had many dedicated flights just for microgravity. We had payload specialists, scientists on board, like me. And we got very, very good results, which are still used today. Of course, after the Columbia accident, the tragedy, there was a hiatus in this program. And today we are using the space station, but not exactly in the same conditions as I mentioned to you. So to finish up, I want to, of course, thank a lot all my crew here. They are here, the French guy is here. They are here. And I thank you for your attention. Thank you.
Merci Jean-Jacques. As we said, we are quite a bit late, so maybe just two very quick questions from the audience, if someone wants to ask something.
So if not, we can discuss in the corridors afterwards.
Exactly, okay. Any quick questions? Or, please.
Yeah.
Did you want to fly to space since you were a child, or this came up later?
That's a very good question. Very good point. No, it came later because, well, I remember with my age, I don't want to talk about my age, but I remember the first Sputnik in space, and more than that, I remember the first flight of Gagarin, who was the first human in orbit, okay? And I remember it very well, but at that time, I considered that these guys, I mean, the astronauts, were just superheroes, you know. I felt not to be part of that, okay? So started science, to study science, engineering, and so on. And later on, the program changed. They opened it to scientists and engineers, and this is when I decided, why not me?
Thank you. One last question, if anyone's in a hurry. Okay. Thank you very much.
Thank you very much.